Hello, good morning, everyone. Sorry for my delay. Let's start. Okay, so next Monday we will have our exam 2. So we have combined the progress of these 2 weeks, this week and next week, together in this lecture summary. So don't worry if you cannot finish the progress this week. Yeah, there is also the next week that you can catch up. So let me start with my presentation today. Okay. So the topic we are going to talk about here is set. So after we have the discussion on set, we will also introduce what is meant by functions. And then if we have time, we will talk about relations. So today it is about set. We will talk about what is meant by a set, and then there are set operations and identities. So these two topics are very closely related to the logic operations and the logical identities that we have. And then finally, we will talk about something that is very interesting, but then it is also a little bit technically difficult. So we will define what is meant by the cardinality of a set and show that for some set, we can call them countable set, and for some set, we call them uncountable set. And then we will give examples for each of these sets. Okay, so what is a set? So a set is simply a collection of objects, and then the ordering among the objects doesn't matter. And then the objects inside the set, we will call them members of a set or items of a set of elements of a set. Now, one way to describe the content of a set is just to list out all its elements. And then we use these big braces, these open and closed braces, to denote the boundary of a set. So here, let's see an example. So we have a brace here, another brace here, open, close. So after enclosing the items inside the brace, then this defines there is a set, and then the items are separated by these commas. So this will be a set that contains 5 items. This is the first one, and then a comma. This is the second one, and then this is the third one, the fourth one, and the fifth one. Okay, so this represents a set with 5 elements. And similarly, this is another set. This set contains 5 elements, A, E, I, O, U. Okay? Sometimes the items inside the set will have a trend, and in that case, we may be using these ellipses to help us to simplify the notation and somehow help us so that we can save some time in writing. For instance, we may be using this 1, 2, ... 9 here to represent the set that contains all the integers starting from 1 up to 9. So the ... represents the missing items. And similarly for this one, so if you see this is a 0 and then -1, -2, there is ... here, and 1, 2, there's ... here. This could be used to represent a set that contains all the integers. And similarly for this one, A, B, C, ... Z, then we may be using this to represent the set that contains all the characters in the English alphabet. And then, but then this may not be a very exact way in defining a set, because maybe, I don't know, maybe there is another interpretation that people may find a set that contains just 1, 2, maybe 8 and 9, something like this. So in such a case, the best way to describe clearly what you want to pick up for the items as a set is we use this set builder notation. So this is nothing special. We use this, so here we have still a brace to represent the boundary of a set. And then there is a stroke here. There's a stroke here. On the left-hand side of the stroke, it tells us that what kind of items will be selected to be inside the set. And then on the right-hand side of this stroke, this part, this will tell us the property of the items that we are selecting. So for instance, I want to select the items of the form of x, and then the property that is related to x is an odd positive integer less than 10. So in such a case, this is a very specific description of what we want to select. And in this case, this represents a set that contains the numbers 1, 3, 5, 7, 9, because these are the odd positive integers that are less than 10. Okay? Or similarly, here, this is the format of the item that we want to select. So it will be of the form of n. And then the right-hand side of this stroke, okay, is the description of the properties of n. So n here is a perfect square. So in that case, we are going to have this set containing the numbers 0, 1, 4, 9, 16, 25, and so on and so forth. And sometimes, yeah, we will, so this is a set that contains nothing inside. So this is something that we call it an empty set. And sometimes for easier notation purpose, we will use this single symbol to represent this set. So this is an empty set notation. Now recall that a set is a collection of items, but then we don't care about the ordering. So in that case, as long as we are listing out the items inside these braces, then in that case, we don't care about the ordering. So 135 is the same as 351. And also, repetition doesn't count. So if I have a set with 1555, this is the same as I have 15. Now, if we want to mean that this is going to be different, that means that the counting of a certain item is important, then in that case, we will use something called the multi-set instead of set. Okay, so but here, when we talk about set, we don't care about the repetition. Now recall that an item inside the set, we usually call it members or elements. In mathematical notation, we usually call it an element. So 5, this number 5 here, is an element of this set, because 5 is a particular item of this set. Now, because 5 is an element, so we are going to use this notation that looks like an E. E stands for element. So we are stating that the relationship between 5 and this set. So it says that 5, this notation says it is an element of the set on the right-hand side. On the other hand, 7 here, if you look at 7, let me see if I can remove this. Oh, no, I can't. So let me enter the full screen again. So here, 7 is not an element of this set, so we are using the notation element with a stroke. So here, this is like the equal and not equal notation. So 7 is not an element of this set. So this is a very simple test of our understanding. So far that we have discussed, if we count carefully how many items can we get in each set, then if you count it carefully and then correct it, then it means that you're quite okay. So for instance, this is a set containing all the integers from 3 to 10, and altogether it is like 10 items missing 1 and 2, so there are 8 items inside. For this one, remember that repetition doesn't count, so in that case, we just have 1, 2, 3, 4. There are 4 different items inside here. Now this one is rather interesting. So it looks complicated, but if you look carefully, this is going to be the first item that we are seeing. And actually, this is the second item. Although these two items are of different type. The first one is an integer, and this second one is a set containing an integer. And then the third one, actually this is the third one. The third one is a set of a set that contains some integer. So this is a big item here. But still, this is a single item. So altogether, this set contains only 3 items. And what is it? Now, this is a notation that represents the empty set. So an empty set is a set without anything inside. So it has 0 items inside. And then this one, this is a set that contains an empty set as an item, as an element. So actually, this set contains one thing. This one thing is this thing. So this set has 1 item inside, which is the empty set. Okay? And then sometimes, okay, so we want to now talk about something called the Russell's paradox. It simply states that, okay, there is actually something not that we will still have some problem with the set builder notation, but nevertheless, yeah, we need to be aware of this. So Russell's paradox begins with, okay, so we have the description here. So we want to say that the objects of a set can be some set itself. So for instance, A is a set, right? So A is a set. It contains one item, the second item, two items, and then three items. So A is a set with three items. Okay, so in that case, now we see that this is actually a set, right? We can talk about this set is an element of A. Yeah, because we can find this as an item inside A, right? But on the other hand, this set is not an item in A. If you look at it carefully, A has three items, this one, and this one. None of them looks like this. So this is not an item of A. Now, notice that for this element notation, we can have a set on the left-hand side and a set on the right-hand side. So in that case, we may use a set builder notation to define something like this. We are going to select items of the form of X such that X is not an element of a set of the set of A. Okay, so in that case, we will see that A has only these three things, and then they are all sets, right? And then we are going to, so for this one, this is defining all the sets such that it is not this one, not this one, and not this one, okay? So it looks like everything is okay. But somehow, how about this? Suppose that we want to collect all the items of the form of X such that X is a set, but then X does not belong to S as an item of X itself. Now it looks natural, right? So it looks like, okay, so for instance, what could be inside this set? Okay, so if you look at this one, this A that we have just defined should be contained inside here, right? Yeah, because A is not an element of A. There are only three elements of A, but A itself is not any one of them, so A is not an element of A. So it looks like naturally we can define something like this. But then with this notation, yeah, so this is another simple example. So for instance, this is a set AB, and then we will see that this is a set, and then it is not contained as an element inside the set. So this should be considered to be collected in this big S here. Everything looks normal, looks natural. But then when Russell asks this question, nobody can answer well. So Russell says, how about S itself? So we have defined S to be this set. This is the big set S. The question here is, can S be an element of S? Now, Russell argues that this is not possible to answer. For instance, let us consider, so we don't know the answer of this question. So let's assume that the answer is yes and see if it is okay. Now, if the answer for this one is yes, then in that case, S is an element of S, right? So because S is an element of S, then in that case, it must satisfy this property, S something S, right? But this is saying what? This is saying that S is not an element of S. So what does that mean? If S is an element of S, yes here, S has to satisfy the property, this property. But that this property is just saying that S is not an element of S. So there is a contradiction. So the answer of this question cannot be yes. It cannot be yes. Okay? How about the answer no? Now, if S is an element of S, the answer is no. That means that S is not an element of S. So S is not an element of S, but so in that case, by this property, what should be contained in S? So if S not S, then it should be here. So if something is not contained in this big set, it means that S and then element S. So if the answer is no, then we will have SES. And SES means what? S is an element of S. So if we start by saying that S is not an element of S, then we will have a conclusion that S is an element of S, and then we again get a contradiction. So what does that mean? It means that something is wrong. Yeah, so this is what Russell is saying. So there is some problem, even if the set builder notation looks very precise, looks very specific, but then we will still hit into some problem here. I don't know how to solve it. So still, I think there are logicians, mathematical logicians, that will try to give an answer for this one. But simply saying is that the set builder notation is not enough to define things precisely. And in the literature, there are some other paradoxes. So there is Barber's paradox, there is Grelling-Nelson paradox, and other examples. So I recommend you to check the Wikipedia for more information. And actually, in the OCW recording, I think I have explained these two things. So if you have a chance, take a look. Now we have talked about sets. So here, let us define some other new type of notation. So the first one is we want to relate two sets, so that we will want to talk about something, the concept of a subset. So if B is a big set, and then A is a set that contains some item that is selected from B, and then nothing else. So A, the item of A is a collection. The items of A are always chosen from B, but nothing else. Then in that case, we call A to be a subset of B. And we use this notation A is a subset of B. Notice that this is not the elements notation. This is the subset notation. So in particular, so for instance, let's say A represents the set of prime numbers, and let's say B represents the set of integers. We see that every prime number must be an integer, so that in that case, A is a set that is choosing items always from B. And then we will say A is a subset of B. We will say two sets are the same if everything appearing in A appears in B, and similarly, everything appears in B appears in A. Okay, so A is the same as B if every item in A appears in B and vice versa. Equivalently, A equals to B if and only if A is a subset of B and B is a subset of A. Yeah, because this says what? A is a subset of B says what? It says that everything appearing in A must appear in B. And this says what? This says everything appearing in B must appear in A. Okay. Now, let's say A is the set of 1, 2, 3 containing this item. So we have a question, is empty set a subset of A? Now, by default, we will say this is yes. Because if you look at the empty set, we check whether every item in the subset, whether every item in this empty set appears in A. Because there's no item, so it is automatically satisfied that every item in, so there is no counter example to say that this is not a subset of A. So in that case, an empty set, by default, we will say that it is a subset of A here, and actually empty set is a subset of any other set. But on the other hand, is empty set an element of A? Now this time it is no, because A contains only 3 elements, 1, 2, 3. None of them looks like this one, so this is not an element. So this question serves two purposes. One is we want to emphasize that empty set by default is a subset of any set, and the other one is the elements notation should not be confused with the subset notation. Okay, the next one is something that we call it a Venn diagram. Venn diagram is introduced in 1881 by mathematician John Venn, and he uses a graphical representation to talk about the relationship between different sets. Usually we will use a rectangle to talk about all the sets that contains all the items that we are interested. So for instance, let's say this rectangle, I give a label n here. This represents the set of all the natural numbers, all the positive integers. Excuse me. My battery is running low, so let me connect it with the cable. Excuse me. Okay. Okay, so here And then we use circle or usually circle or what? Or the ellipses, yeah, to represent a certain subset of the big set. So the big set, the blue part here, the rectangle, is called the universal set. It is like the universe. It contains everything. So the universal set represents a set that contains all the items that we are interested. And the circle here represents a subset of the universal set. So for instance, we can have this green circle. Green circle represents odd. So everything inside this green circle are the items that we're interested for this green part. So we should have all the odd integers inside the green one. And in that case, all the even numbers should be outside the green part. So we will see 2, 4, 6, and 8 outside the green part. And then we can similarly draw a red circle here for representing another subset of the universal set. And this set's prime. So we are going to collect all the primes inside the red one. So this part inside here will be the common item of the green and the red set. So we will put the common items inside here. Okay. Now, once we have the Venn diagram, it is easy to talk about several set operations that we want to do. Set operations are creating new sets based on existing sets. So the first one is called the union. The union of two sets is a set that contains all the items in A or in B. So it is like A or B. Any item in A or B will be collected in the union of the set A and B. Okay, so the notation here is A with a U and then a B, A, U, B. So U stands for the union. Is that okay? And similarly, we have the opposite. So this time we focus on the common part. So we call this the intersection. The intersection of two sets A and B, they are represented by A and B. So A intersects B here. So this is the common part, the shaded part represents the common part of the set A and B. So it collects all the items that appears in both A and B. So this is called the intersection. And then we have the complement. So if A is here, then the shaded part here is something that is the complement of A, which is containing all the items that is not in A. And then we can also talk about the difference. Oh, the difference here is not a symmetric operation. The difference of A and B, we denote it by A minus B, is we start from the set of A, but then minus B, we take away everything that appears in B. So with A here and take away things that appears in B, so we will have this remaining part, the shaded part. This is denoted by A minus B, the difference of A and B. So A minus B in general is not equal to B minus A. So a good question for you. So when will A minus B equals to B minus A? Yeah, think about this. Another set operation is called the power set. So the power set of a set A, we denote this by 2 to the power A, is a set that contains all the subsets of A. So if A is 0, 1, then based on this set of A, then we can find out, what kind of subset of A that we can form. A subset is a set that is formed by taking some of the items of A. So empty set is a subset. This set containing just the 0 is a subset. This set containing just the 1 is a subset. And A itself is also a subset. So we will see that this A has 4 subsets. And the set containing all the subsets of A is called the power set of A. And you will see that why we want to choose this notation. Okay, if A has n items, exactly n items, so how many items will there be for the power set of A? We can easily compute it by using rule of product, that the possible number of subsets of A is 2 to the power n, because for each item, it will be selected or not selected in a particular subset of A. Okay, so every item has 2 choices, so altogether 2 to the power n, different ways of forming a subset of A. Okay, And the next part are something that is extremely similar to the logical equivalence identities that we have. So we have the identity laws. So if A intersects with the universal set, then it becomes A. A union of the empty set, it is still A. So it is like if I have a logical statement P, if it is n true, P n true, so it is like true, P n true is P, P or false is still P. And the domination law is if I have a set intersect with the empty set, the common thing must be empty set. And similarly, if I have a set, I'm union this with the universal set, then I will get everything. So it is the union set. It is like if I have a logical statement P and false, P and false will be false, and then P or true will be true. And we will also have something of the idempotent laws. So the same thing, if I applied it, the same set, if I applied it on itself many times with an and or, then we still get the same thing. A and A is A union A is A. Okay, A intersect A is A union A is A. Just like P and P is P, P or P is P. Okay, complementation law. The complement of the complement is itself, so it is the double negation law. Okay, commutative. So A intersect B is the same as B intersect A. A union B is the same as B union A. We also have the associative law. So associative law is we have different sets, but then in between them we are using the same operations. So A intersect bracket B intersect C is the same as A intersect B first and then intersect C. So the associative law allows us, because the ordering of computing which part doesn't matter, so we can omit the bracket when we are talking about a lot of things with the same operations applying together. Okay, union is also the same. Okay, and then we also have distributive law, and then De Morgan's law, absorption law, and complement laws. So if you check each one by one, then it is really, there is a one-to-one correspondence with the logical equivalence identities. And how do we prove this? So to prove logical equivalence, we use a truth table. And here we have something that is really similar. We have a membership table. So the membership table specifies checking when an item is, when a certain object, let's say of the universal set, is in A or in B or whatever, all the different possible cases, we will find out that this item is on the left-hand side of set if and only if it is on the inside the right-hand side of the set. So somehow we will see that if these two things agree, then we will say that this one and this one, they are representing the same set. So yeah, check the OCW recordings for details, but this is a high-level idea. We can prove the identity of two different operations of sets to be the same, yeah, by using the membership table. Also, we can use words to argue things. Also, we can apply known set identities to help us. So these are the same technique that we have used before. So check the OCW recordings for details. And now, we are now finally moving to the hard part of this lecture. We now introduce the notation, the concept of cardinality of a set. So cardinality of a set simply talks about how large of the size of a set is. So if there are n distinct items in the set of A, then and n is a non-negative integer, then in that case, we will say the set of A is a finite set. It has a finite number of items. Is that okay? And then n itself is the cardinality of A. The notation of cardinality of a set is simply we put an absolute notation, so a bar on the left and the right of a set to represent the size or the cardinality of A. So in this case, so we have an example. A is a set here, and then it contains 0, 1, orange, and apple, so there are 4 items here. So the cardinality of A is equal to 4. This is a special case. So here, when the size of A, when the size, when the number of items inside A is finite, then in that case, the cardinality is equal to the number of items inside the set. But if a set is not finite, then we still want to define what is meant by the cardinality. But at least, if a set is not finite, then in that case, we will simply call it an infinite set. So there are some examples. For instance, the set of natural numbers, which contains 1, 2, 3, 4, 5, okay, up to a lot of numbers, right? So we will see that it is not a finite set. You can't say that, oh, there is a number that can tell us, okay, exactly how many items inside here. No, it has infinite number of items, so it is an infinite set. And the set of real numbers is also an infinite set. Because actually the set of real numbers contains the set of natural numbers, right? So set 1 here is a subset of set 2. So somehow the size of set 2, the items of set 2 should be at least the same as the number of items in 1. So if 1 is infinite already, then 2 must be infinite. And what I want to say here is that mathematicians not just want to define the cardinality for finite sets, but they also want to define the cardinality for infinite sets. And of one particular set, they find it very important. It is the natural number set. Natural numbers contains all the positive integers. Although it is the number of items inside is infinite, we still want to capture, somehow give a notation of the size, the cardinality of this set. So we will use this notation, R 0, R 0, to represent the cardinality of the natural numbers. And why do we want to talk about this? It is because somehow, once we have the cardinality of the natural number set defined, then we may be finding some other set which has the same cardinality as the set of natural numbers. So we want to do some comparison of the size of 2 different sets. Now, how do we compare the size of infinite set? Yeah, because everything is infinite, right? So in order to compare the size of 2 infinite sets, we use a very simple idea. We just check if there is a 1-to-1 correspondence between the items in a set A and the items in the set B. So whenever we pick an item in A, can we always find a specific item in B so that they form a pairing? So if it is always found, any item in A can be found with the pairing of an item in B and vice versa, then in that case, we will say that these 2 sets, they have the same number of items. They have the same cardinality. So we will write the size of A, or the cardinality of A, is the same as the cardinality of B. So we want to ask, which of the following sets have the cardinality of R 0? First of all, the English alphabet is not having the cardinality of R 0 because the English alphabet has a finite size, but R 0 is infinite. So we can't form a 1-to-1 correspondence. So somehow, for each item here, we want to have a distinct item in the English alphabet to correspond to it, but somehow we find that there are more than 26 numbers of items inside this infinite set natural numbers. So in that case, the set of natural numbers cannot form a 1-to-1 correspondence with English alphabet. But how about the set of non-negative integers? This time, yes. How? So the 1-to-1 correspondence is like this. So we start by looking at the number. So we want to show that there is a way that we can correspond numbers of negative numbers inside this set with the numbers inside the natural numbers. So the correspondence is we start from 0 here, and then which is mapped to 1. And then we look at 1, which is mapped to 2, -1 mapped to 3, 2 map to 4, minus 2 map to 5. So we are listing the items here one by one, starting from 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on and so forth. Now, because we can list out all the items here one by one, that means that we have a correspondence of the numbers here with the natural numbers. The first item listed will be corresponding to 1, the second item listed will be corresponding to 2, and so on and so forth. In that case, excuse me. In that case, we are actually counting out the items here one by one. If we can count out the items here one by one, and then the number of items here is corresponding to, can have a one-to-one correspondence with the natural numbers, then this is nice. Okay, it will have the same cardinality as the natural number set. Is that okay? And then this one, okay, the set of integers. Okay, set of integers. Sorry, the set of non-negative integers, I make a mistake. I am just talking about set of integers here just now. So if we count things like 0, and then 1, and then minus 1, and then 2, and then minus 2, and so on and so forth, so every number will be counted. The set of non-negative integers is even simpler. We start by counting things from 0, 1, 2, 3, 4, and so on and so forth. So we will see that every item inside this set can be counted out. Okay. The set of even numbers is also okay because we can count things out by looking at something like we start from 0, and then 2, and then minus 2, and then 4, and then minus 4, and so on and so forth. And in fact, the set of even numbers is a subset of the set of integers. So that means that the size of this one is no more than the size of the set of integers. On the other hand, the set of even numbers is also an infinite set. So in that sense, the combination of these two statements together means that it will have the same number of items as the set of natural numbers. Okay. Now 5 talks about, maybe something wrong. But then, the best way to show a set has the same cardinality as a natural number set is to list them out one by one and show that, there is a one-to-one correspondence with the natural numbers. Okay, the next one is the set of rational numbers. For this one, it requires some drawing, so please visit the OCW recording for details. And finally, this is important, okay? The set of real numbers is an infinite set, right? It has infinite number of items. And then we want to show that this is special. It has far much more items than the natural number set. So the cardinality of real numbers is not going to be the same as the set of natural numbers. Okay, so this is the main topic that we want to talk about today. Okay. So before we move on, I want to talk about these two adjectives to describe a set. So we have described a set by classifying them as finite set and infinite set based on the number of items inside. But then we can also classify sets talking about countable set and uncountable set. So countable set is the set that is a set such that we can count out the items inside it. Excuse me. Count out the number of items. Count out the items inside one by one without missing. So if a set is finite, then naturally we can count out things one by one without missing it. After some steps, we will finish counting. So in that case, we call it a countable set. Another set that we are interested is the set that has cardinality Aleph naught. If a set has cardinality Aleph naught, then we can count out the items one by one as we shown just now. And then this set is also called a countable set. But then for sets that is not these two types, the number of items is much more, so that there is no way that we can count out the items inside the set one by one. then the set is called uncountable. Now, amazingly, showing things to be countable is easy, right? It is because we just need to find a way to count things out. But how do we show things to be uncountable? So somehow, the idea here is to show this by contradiction. In 1891, Georg Cantor, a German mathematician, he showed that the set of real numbers is actually an uncountable set. So how does Cantor show that this is uncountable? Okay, the proof is by contradiction. And in particular, we don't need to worry a lot about the set of real numbers. We worry just only a specific subset of the real numbers. Let's say we focus on the numbers that is on the real numbers that is in between 0 and 1. If this set of numbers, this set of real numbers is already uncountable, so that there is no way to count things out even for only this restricted set, then the bigger set of real numbers must also be uncountable, right? Yeah. So what Cantor is showing is just this set is not countable. Okay, so to prove it, then we are going to use contradiction. So suppose on the contrary that this R prime is this set of real numbers inside 0, 1. This R prime is countable. Then what does that mean? If it is countable, then that means that there is always a 1-1 correspondence between R prime and the natural number set n. So in that case, if it is countable, someone, a genius or a god, can give us a way to list out the items in R prime one by one without missing. So we are going to list out the items one by one without missing. So it could be something like this. This is just an example. The god or the genius may be listing out the items one by one. So this is a real number in 0, 1, another real number in 0, 1, and so on and so forth. So we can list out the items here one by one. Now, based on this listing, then we are going to show something wrong. What we are going to show is that we are going to construct a number, let's call it x here, such that I want this x to be special. I want the first decimal place of x is not the same as x1. I want the second decimal place of x is not the same as the second number that we are listing, x2. And so on and so forth. The third decimal place is not the same as the third decimal place in x3, and so on and so forth. So how do we do this? So if it is odd, then I put an even number here, 2, let's say. If it is even, then I put odd. If it is odd, then I put even. If it is even, I put an odd. Is that okay? So in that case, we will see that this number x cannot be equal to x1, cannot be equal to x2, cannot be equal to x3, and so on and so forth. X will not be listed. This number x will not be listed because let's say someone says that, oh, x is listed as a 10,000th item, but then the 10,000th decimal place of x is not the same as a 10,000th item. So in such a case, we find that x is not listed. But on the other hand, if you observe things carefully, this x actually is an item between 0 and 1. So we now have a contradiction. The contradiction says every real number between 0 and 1 should be listed, but then here we just say that we just found out that x is not listed, so there is a contradiction. Okay, when there is a contradiction, there must be something wrong. What is wrong? It is this part that is wrong. We suppose on the contrary that R prime is countable, so this is wrong. And because this is wrong, so what is right? The right thing is R prime is uncountable. R prime is uncountable. It means that the bigger set that containing this R prime is also uncountable. Okay, this is the hardest part for today's topic. And finally, we want to talk about the principle of inclusion and exclusion. So here, suppose that A and B, they are finite sets. You can easily argue that the size of A union B is the same as the size of A plus the size of B minus the size of A intersect B. Reason, very simple. If you look at this, look at this figure. This is giving us the proof. I want to count how many items are there in this union part, A union B. So we can take a look of how many size, the size of A plus the size of B, we add them up together. But somehow, the items here in the intersection part, they are counted 2 times. We should count them once, but we are counting them twice. So we should minus it, deduct it. So that's why we have this inclusion-exclusion thing. And then we can generalize this for the case where we have 3 sets A, B, C. So it is like A union B union C. We want to get the size. So what we can do here is that we just simply add up the size of each individual set, add them up. But then some parts, they are overcounted. So we should minus what? Minus the common part of AB, minus the common part of AC, and minus the common part of BC. But then, these are things that we try to deduct, to remove, but then we are removing too much. So somehow, some things are overly removed. We should add back. So what should be adding back? So it should be adding back the part that is the common part of all the 3 sets. So this is the case where we have 3 sets. And similarly, or in general, for K sets, K different sets, or they could be the same, whatever, but for K sets, the size of the union can be computed by the size of the individual one adding up together minus the common part of any 2 sets, but adding back the common part of any 3 sets, and then minusing the common part of any 4 sets, and then adding back the common part of any 5 sets, and so on and so forth. And this is called the principle of inclusion and exclusion. How do we prove it? Yeah, let's make it a homework exercise for you. So we can prove this easily by combinatorial argument. And finally, there is an example. So we want to find out how many integers between 1 and 250 that are divisible by the numbers 2, 3, 5, or 7. Okay, you can count things out. And similarly for this one, this is another counting problem. So I'll leave this as an exercise for you. Okay, sorry for making this lecture very long. Yeah, this is going to be used for 2 weeks. Okay, and then yeah, that's all for today. Thanks for coming. And then we will have, for next week, we will talk about the exam 2 solution on Wednesday. Okay, thank you very much. Okay, see you, and then good luck to the exam.